Okay, good afternoon, everyone. Good afternoon. Good afternoon. Okay. So as I mentioned a couple of times in some of those long emails which nobody reads, I came a little earlier and then I drew all these on the board. Okay, these are all things that we've seen in the previous lecture. Okay, so this will help us save some time. This is the problem we started off with last class. Okay, we have this multi-degree of freedom problem. Okay, here I have a mass m1 which can translate horizontally, and then I have this springy pendulum which is capable of performing multiple degree of freedom motion. The steps that we took to solve this problem were the following. First step is we look at the static equilibrium position. At the static equilibrium position, the spring here was deflected statically because of the weight of the ball. Okay? We performed the force balance and we got this particular expression right here. Then we decided on the number of degrees of freedom, and intuition, common sense tells us that the mass can travel only horizontally, so it has 1 degree of freedom, mass m1. Then the springy pendulum, because it's not a string, it's rather a spring, it has 2 degrees of freedom. Okay, and it's restricted to motion along the xy plane, okay, along the plane of the board. So those 3 degrees of freedom are marked in the figure here, x of t, theta of t, r of t. Okay, they are all functions of time. From now on, if I write x, if I write r, if I write theta, it is understood implicitly that they are all functions of time. Okay. Once we did that, we delved into dynamics, ME 2030. We looked at radial transverse coordinate systems. Okay. I know that this is a point of concern for some of you, because being dynamics is taught in different dynamic ways by different dynamic people. So hopefully we will all have a common way of solving these problems as we solve a few more in class. We set up the accelerations. The acceleration of this block, the acceleration of the pendulum bob. The thing I want to emphasize is these accelerations are always written with respect to an inertial observer. The reason being, Newton's laws are valid only in an inertial frame of reference. The best example of an inertial observer is a stationary observer. So typically a fly on the wall is a stationary observer. So for us, point O here acts as the inertial observer. You write your accelerations with respect to that particular observer. It's easy to write this one. It is just translational motion. The tricky one is the acceleration of the bob, which is B here. We set up a coordinate frame. At the point A, I have an observer. That observer is looking at the motion of the bob by means of this ER, E theta coordinate system. Okay? But that's not an inertial frame. Why is that? Because this is attached to the pendulum. The pendulum is accelerating. So I do not want to write my acceleration of the bob of the pendulum as just the acceleration of the bob seen by the observer at A. It has to be with respect to a stationary observer, and so we use the triangle law of addition of vectors, which we saw in the last class. And then we eventually come to this particular expression here, which is written on the bottom of the board. Acceleration of B slash O, x double dot in the I hat direction, which is the horizontal direction. And then I have the rest of these crazy terms, one of them coming from motion in the radial direction, the other coming from motion in the transverse direction. But our job is not done. Why is it not done? It's because, as I mentioned last class, this is in the I hat system. These are all in the ER and the E theta systems. So we need to perform a coordinate transformation so that they are all in the same coordinate system. It could be the IJ system, that's fine with me. Or it could be the ER, E theta system, that's also fine with me. You do what is the easiest one to do. Okay, and the easiest one is transform I hat into components along ER and E theta. Why is that easy? Because I need to do it only once. That's the only reason. There is nothing else, no physics-based reason here for my thought process. Okay? Yes, question.
Will this be provided?
Will this be provided? No. No, this won't be provided, okay? Because the exam is open book, open notes. Okay, so I won't be giving you a formula sheet. Right? Does it make everybody happy? So you keep me happy, I'll keep you happy. All right. So moving on. See, what I want you to take from this course is the foundational aspects of dynamics, how to apply that to practical problems. You go to the field, you go to your work, you go to an industry, they're not going to ask you, okay, solve this problem. I'm not giving you solutions because there are no damn solutions to the problem you're going to solve. There are no formula sheets that are going to help you. It's your thought process that's going to help you. Okay? Alright, so moving on. That's my spiel for today. X hat, I hat, X double or I hat, converted into ER and E theta. Watch this carefully. You've done this before. We're going to do this multiple times in the future. Here is how I do it. I draw the I hat unit vector. I draw the ER direction, I draw the E theta directions. They are drawn in the directions I have initially chosen in the problem. Then, I mark the angle theta. If this is theta, then the angle here is 90 minus theta, which means that this angle remaining here is theta. Once I do that, finding components is something you've done in statics. It is nothing but projecting a vector into two other directions. So what do? I take the vector I. From the head of this vector I drop a perpendicular to the E theta, I drop a perpendicular to the ER directions. And then the projection, which is given in this slightly different color, is the magnitude of the vector I hat. What's the magnitude of I hat? It's 1. Multiplied by the cosine of the angle between the direction I'm projecting into the vector I'm projecting that onto. So here it's cosine of theta. This angle is 90 minus theta. Cosine of 90 minus theta is sine theta. The projection is going to be I hat times sine theta. Somebody kept a bucket here. Does this make sense to everybody? The coordinate transformation. Are there any questions on that? I want to ask right now. We're going to do more problems where we will do this in real time. But I'm not going to spend too much time on it. There are enough resources I've uploaded on Carbon. Okay, if you have other questions, happy to answer them during office hours or after class as well. Once I did that, this is the byproduct of that coordinate transformation. And then all I have to do is stick that into x double dot times I hat. So wherever I see an I hat, I substitute sine theta E theta, ER plus cosine theta E theta. Once I did that, my last step here was just to collect all the terms of the acceleration in the ER direction, all the terms of the acceleration in the E theta direction. This beast is the one that we are going to work with. You see, I have labeled two things there. This collective term in the radial direction is the radial acceleration. This collective term in the transverse direction, theta, not the tangent, the transverse direction is the transverse acceleration. Okay? And it also makes common sense. Just one more minute. If I look at the definition of R of t, capital R of t, L2 is a constant, delta is a constant. So if I differentiate R, it's going to be R dot. So note that R dot is the same as little r dot. R double dot is the same as little r double dot. Okay? I'm not going to go through with that substitution. We'll just stick with capital R. That's good enough for us. Alright. Now, I'm going to do the force balance, okay, which is the event that we are waiting for. I will complete it, and then I will take questions. Now we come to the kinetics part of the problem. First thing I'm going to do, I'm going to look at this springy pendulum. Okay? I'm going to look at that spring that connects the bob of the pendulum and the mass. So here is my figure for that. and I want to stress this very, very clearly. The directions or the coordinates that I want, theta of t, r of t, and x of t, this does not tell me that the body is moving to the right. This does not tell me that the pendulum is swinging counterclockwise. It does not tell you that at all. What it tells you is if the mass is moving to the right, then x of t is going to be positive. If the pendulum is stretching radially, r of t is going to be positive. And if the pendulum is swinging counterclockwise, theta of t is going to be positive. It does not in any way tell me this is how the system moves. What tells me how the system moves is the equations of motion. I solve those equations, which we cannot because they're going to be nonlinear in this problem. But if we do solve it, they will tell us how the system moves. Okay? So with that said, for positive r of t, positive x of t, okay, this is the displacement of the mass m1, this is the displacement of the pendulum. You can clearly see that the displacement x of t is not along the length of the spring. Springs do not like that. So they will say, hey, I'm going to take only displacements along my length, so I'm going to take this x of t and I'm going to break it up into its components. One component along the length of the spring, and another component that is perpendicular to the length of the spring. The angle here is theta, which tells me by geometry that angle is also theta. So if I break x of t into its components, I'm going to have x cosine theta along one direction here, and this guy is x sine theta. And so in reality, the spring is going to feel the following displacements. So this r of t, x times sine. This is spring K2. And so if I now write the spring force, okay, Fs2, I'm going to do it here. This is the spring force after the spring has been put into motion. Please notice this. Focus on this second figure here. For positive r of t, for positive x of t, and for positive sine theta, if r of t is greater than x times sine theta, the spring is going to be in a state of tension. Okay? So that means I'm going to write all these down. So this is K2 times the portion that's in tension minus the portion that's in compression. This is for r greater than x sine theta. The spring is in tension. But here is what we're going to say. Okay, I'm looking at springs, which means that the condition that their deformations are elastic should not be violated. Sine theta is an angle that can swing wildly between 0 and 1, which means we are going to assume that all motion is very small. Okay, so for small motion, which tells me that x of t, r of t, theta of t are all small, and under this umbrella sine theta becomes theta, and cosine theta becomes 1. Does this make sense to everyone? Small angles, right? Small angle, small motion. And so from that point of view, if I look at the spring displacement now, you see what happens. Fs2 is now approximately r of t sin theta becomes theta, so this is x times sin theta. Sin theta becomes theta, sorry. Can I simplify this further? Okay, here is a question. I have a small number. I have another small number. I multiply the two numbers together, their product is going to be an even smaller number. Which means if x of t is small, theta of t is small, x of t times theta of t is minuscule. So I'm going to completely get rid of that creature. Alright, so that's taken care of. Then the next obvious question is, okay, what about that x cosine theta term? Because theta is very small, cosine theta is approximately 1, which means that the direction of x cosine theta is not as exaggerated as I have drawn, it is approximately along the horizontal. And that is taken by the other spring, which has a stiffness K1, you see? So x of t is actually prevented from moving further by this spring K1, which will exert a restoring force back on the mass. Okay, so x cosine theta is accounted for, becomes x of t, and this is taken by spring K1. Does this make sense to everybody? So all the displacements are accounted for. We are assuming small motion in system dynamics in 3260, and for the major part of 3360, you're going to assume small motion. What you will see later on in control systems is that obviously these are all errors, right? Sin theta, you really cannot say it's an infinitesimal quantity. It could be a finite quantity. So these will be categorized as disturbances to the system, and you will design some kind of a control system or a controller that will be able to account for the disturbances by means of feedback compensations and so on. This is something you'll see in 3360, okay, not here. I draw the spring and the damping element here, the other one. This is K1. This is C. For a positive x of t, the spring is in tension. Fs1, Fs1. For a positive velocity x dot, the damping element is always stretched, so that's going to be Fd. Fd. I have the mass attached to these, so the mass is going to face these following forces. It's going to have an Fs1 equal and opposite and Fd equal and opposite. I'm going to redraw these figures, especially the mass, again in a new panel. This is Fs1. This is Fd. There was an applied force acting on this block M1. Okay, so this is block M1. F1 of t is an external force. I have the weight. M1g. Anything else that I'm missing? Yes? Normal, okay, normal, okay. I'll come back to you. Normal, okay. Yes? You had
spring force 2.
Absolutely, spring force 2. Okay? So the spring was acting Fs2, Fs2. That end of the spring that I've circled is connected to the center of the block, so I'm going to have an Fs2 equal and opposite. This is the free body diagram of the block. I'm going to redraw it, and I'm going to draw the free body diagram of the pendulum as well. Okay? I'm going to slide this panel up while I bring the other one down. free body diagram of the block, the free body diagram of the bob of the pendulum, okay? A kinetic diagram of the block as well, and kinetic diagram for the bob of the pendulum. So free body diagram. You don't need to write this again because you've drawn this there. Fs1, Fd, F1 of t, normal force, m1 times g, I have the spring force, which has to be broken into its components along the horizontal and the vertical, because I'm interested in motion only along those directions. So the spring force here, Fs2, okay. We have the angles and so on. Theta of t is the angle, okay. So I break it into its components. That's Fs2 sine theta and Fs2 cosine theta. Perpendicular. This way, I'm sorry, and the horizontal. This way. Okay, so that's going to be Fs2 cosine theta and Fs2 sine theta. Normal force is there, mass is there, acceleration due to gravity is there. Then the kinetic diagram for the block is fairly straightforward, it's simple. M1 x double dot. This is the positive sign convention that we chose. Once again, this does not tell you this is how the block moves. No, it tells you if the block moves this way, the displacement x of t is positive. If the pendulum is swinging the way it is drawn, then the displacements theta and r are positive. Okay. All right. Fs2 sine theta is approximately Fs2 times theta. Does this make sense to everybody? Sine theta is small, right? So we are assuming that this is for small angles. Fs2 by itself was k2 r of t minus x times theta, but the x times theta was, I have a spider living on my shirt here. X times theta is small, so this is just k2 times r of t times theta. What do we do with this thing? Yes.
Wouldn't r times theta be very small?
That's also small, so get rid of it. The argument is this. Sine theta is small, so sine theta becomes theta. Fs2, because of the small nature of x and theta, became k2 times r of t, but r of t times theta of t is also the product of two small numbers, so that quantity vanishes, and Fs2 cosine theta becomes approximately Fs2, and you can see now that for small motion, the spring of stiffness k2 is not contributing to the motion of the block m1. This is for small motion, okay, under the realm of elastic deformation. So with that said, I'm going to write the equation of motion for this block system. Then we will go to the pendulum. Okay, I'm going to sum forces in the x direction on the free body diagram and the kinetic diagram. Forces on the free body diagram, sign convention. I have the spring force Fs1 Fd pointing opposite to the sign convention, so this is minus Fs1 minus Fd plus F1 of t. These are all the relevant forces. Fs2 sine theta does not contribute to any action, so I can get rid of that. This is just equal to m1 x double dot. Fs1 and Fsd from before, the figures have been drawn. K1 times x c times x dot and so I have m1 x double dot c x dot k1 x is equal to f1 of t. This is pretty nice because it looks as if the block M1 is not at all attached to the pendulum. There is no effect of the pendulum on this block at all, which is weird, right? It's as if it's its own being, having the powers to attract only the pendulum but not itself. Okay? But this is all because of small motion. This is valid only for very small amounts of deflections from the static equilibrium position. So please take this very carefully with a pinch of salt. If I do the force balance in the other direction, I want to make this point here. Force is pointing upwards. If I do that force balance, you see what happens. I have the normal force minus m1g, and I have probably Fs2. There are two equations here, and I want to make this point very, very clear. Even though there are two equations here which are a consequence of force balance, there is only one equation of motion. This is the equation of motion. This equation here is called the constraint equation. It is not the equation of motion. Okay? So any force balance or moment balance that you perform, if it contains a constraint force, what's a constraint force? A normal force, pin reactions, the tension of the string, these are all constraint forces. If any equation contains a constraint force, that equation is not the equation of motion. Okay, because constraints are not known a priori. You have to solve the equation of motion first to obtain what the constraints are. Most of the times, except in this particular case. But in that case, you do need Fs2, which comes from the equation of the pendulum. Okay, so this is the constraint equation. The common constraints, I'm going to write that here. Typical constraints. Normal forces, normal reactions. Then you have pin reactions, okay, support reactions and so on. Pin or support reactions. And most importantly, I want to maybe add that statement here. Tensions. So they're all constraints. Okay? Those are the three constraints that we will see in system dynamics predominantly. You're going to see pin reactions and so on later on. Normal forces you already see. Tension you're going to see in the problem I'm going to solve right after this one. Okay? Alright, so that's the equation of motion. This is the constraint equation. In many problems, you will be asked to find only the equation of motion. Don't waste your time calculating the constraints. This is one of the biggest banes of Newtonian mechanics. You have to deal with the constraints. If you go to Lagrangian mechanics, for certain types of systems called holonomic systems, you can very beautifully solve the problem without drawing any free body or kinetic diagrams, without doing any figures, without worrying about any constraints. you will just end up with this guy. One of you had a question, yes?
Why do we not account, is there any static force that's due to gravity at rest?
There is, yes, I think I should have pointed that out. So yeah, you're right. F2, Fs2 static, right, from SEP. That's right, that's a good point. So that's going to be here. This is, I'll add that here. Thank you for pointing it out. Minus Fs2 static is equal to 0, but it does not affect the dynamics of the problem. Just is taken care of by the constraints. Yes?
Why can we do small angle analysis here?
Why can we do it is because we are using spring elements, and spring elements deform only elastically. So if any deformation is elastic, you would have seen in a stress strain curve that the strains are less than 0.02%. At the very maximum, they are 0.02%. Okay? So those deformations are really, really small. Hooke's law is only valid in that small deformation regime. If the springs are deformed plastically, Hooke's law is no longer valid. You have to use plasticity theory. Yes?
So for this small motion, it's almost as if this spring was just a string and it didn't have any ability to deform?
Oh, it does. It's going to affect the motion of the bob of the pendulum.
Okay.
You see. It's not going to have any bearing on the motion of the mass as such, except in the constraint forces. But I'm not worried too much about the constraints, you see. Okay, last question and then I'm moving. Yeah, go on.
Yeah, I just wanted to double back on like the crossing out of the beta and K2 RT beta T. How did you get RT beta T? Oh, right here, Fs2 equals 10. Okay. I don't know.
I'm going to bring the panel down. All right, now we go for the pendulum bob. Okay, I'm going to answer the question then. Okay? Hang on, let me complete the pendulum. So I'm going to have the free body diagram of the pendulum, the kinetic diagram of the pendulum. Okay? So here is the free body. Please watch this carefully. This is the first time we're doing radial transfers in this semester. So the kinetic diagram, I marked the positive mass times acceleration components. Okay, and we had it somewhere, we had erased it, but I hope you have it in your notes. This was positive ER, positive E theta, positive ER, positive E theta, mass times acceleration in the radial direction, and in the transverse. And for your convenience, we will write out AR and A theta once we write the equations of motion. Okay? Free body diagrams. Pride of place goes to gravity. Always. This is M2G. Then I'm going to have the spring force. You will see that the bob of the pendulum, if I go back here, was attached to this point on the spring. So I'm going to have a spring force equal and opposite to that on the bob of the pendulum along the radial direction. This is Fs2 plus Fs2 static. This is the net spring force. Okay. This is the radial and the transverse. And I had this applied force F2 of t, which was acting in the horizontal direction at all instances on the bob of the pendulum. Okay, this was there in the figure that we had last time during lecture. There were two forces acting, one on the mass, one on the pendulum. Okay? This force is always horizontal. Those are the only forces as far as we can recollect. Alright, now we have to break everything into components. Okay? First things first, this angle is theta. means that this angle here is also theta. So I'm going to take M2G, break it up into components along the radial and the transverse, the positive radial and the positive, negative transverse. This is M2G cosine theta, M2G sine theta. I hope this is clear to everybody. Just taking a force, breaking it up into components. Okay, nothing magical happening here. I do the same thing for the force F2. As you can see, that's also going to be broken up into components. One this way, one this way. The angle here is theta. Right? So the first component is F2 cosine theta. And this is F2 sine theta. So F2 broken into components along the theta and the r directions. Now we are ready for the equations of motion, all of them put together. Okay, so I start with the radial direction. Sum of forces on the free body diagram, the radial. Sum of forces, kinetic diagram, radial, positive radial directions. This is my notation. Okay. Look at all the forces. M2G cosine theta. We're going to use small angles, so very soon some of these will become a little different. Then I'm going to have minus Fs2 minus Fs2 static. Then I'm going to have plus F2 sine theta. This is equal to m times AR. Yes.
FS2 static.
You can, but let us assume that more or less that's always going to be in the radial direction along the length of the spring. So that's a component that's carried through. If you really want, you can break it up into components and you'll figure out that it's only this component along the radial direction that will cause anything. It will be Fs2 static times cosine theta. The one along the transverse will be Fs2 static times sine theta. And that will be very small. Cosine theta. So the question asked was, is Fs2 static not broken into components? You typically don't need to worry about it because we're going to make use of small angles. You're going to see in a minute it's going to vanish. Okay? M2G cosine theta is just M2G. Cosine theta is 1. Fs2 is K2 times RT minus Fs2 static, which was approximate, plus F2 sine theta is F2 times theta, which is a weird thing, as you will see, is m times r double dot r theta dot square x double dot sine theta. M2G, Fs2 static cancel off from SCP. That does not contribute to any motion. Okay? So I'm going to have K2 r of t brought onto the other side. Sine theta becomes theta, so I have the following. M times r double dot r theta dot square x double dot theta of t plus K2 times r of t you see something weird happen. What's F2? F2 is an applied force, right? It's an external force. But you also see that F2 is clubbed together with this dependent variable theta of t. Which means that if I bring it to this side here, because it's a dependent variable, I have all my dependent variables and their derivatives on the left hand side. F2 does not become a dependent variable. What happens is that I now have a time varying nonlinear system, because this is now acting as if it's a coefficient for theta of t. This is not by design. Okay, this is because of the small angle approximations and the inherent nonlinearity of this really chaotic system. This is a system that exhibits chaotic. Of course, we are not going to solve it, but this is a good starting point for going into complicated things. One more time, I want to make the point, and one of you had your hands raised, and I want to answer that question. I have done one thing here. I brought F2 times theta of t onto the left-hand side of the equation, because the standard form is I write all variables that are the dependent variables and their derivatives on the left-hand side. So in the process of doing so, this guy becomes a coefficient for theta of t, which makes this a time varying system. The system is nonlinear because the dead giveaway here is theta dot square. Okay, that's nonlinear. Okay, and there is another nonlinearity here. It's x double dot times theta of t. That's another nonlinearity. Don't make the mistake of cancelling theta dot square. If theta is small, it does not mean that theta dot is small. Okay? If the velocity is 0, it does not mean that the acceleration is 0. I take a ball, I throw it up in the air. Right when it reverses direction, its velocity is 0, but its acceleration is equal to that of gravity. Okay? So cannot make those changes there. This is inherently nonlinear. Question? Answer? Okay, fantastic. Yes.
Can you explain again why FS2 is static?
Oh, because from SCP, this and this are equal to each other.
Okay. Yeah.
From SCP, we had done the SCP analysis at the beginning. M2G is equal to F2 static. Okay? Next one. Few more minutes. Okay? Last force balance. Do you still like this board approach, or do you want me to use my iPad? Board? Okay. Gives you a chance to also talk to each other as I'm erasing. Yeah, I did not mean that literally. Okay. Please focus. We have one more thing. Force in the transverse there. All right. There are some ghost letterings here. What are the forces? I look at my free body diagram there. That's minus M2G. I'm going to start taking some liberties. Sine theta is theta, approximate a small angle, so this is just going to be theta of t. Okay? Then I'm going to have F2 cosine theta. Cosine theta is approximately 1, so I have made use of the approximation that cosine theta times F2 is just F2. Okay? Sine theta is theta. And then I have nothing else. This is just equal to mass times acceleration there. So once I have all this, I just write out the entire set of equations, rearrange everything. So ma theta